So now we're going to take a look at rotational dynamics. We looked at rotation kinematics for the most part within the circular motion unit. We did look at some parts with forces, but now we're going to take a look at dynamics and go a little bit further with looking at objects that are moving in a circle. So on a bike, if you have a speedometer, the way this works is there's a small magnet and there's a sensor that's located somewhere on the bike itself. And so as the tire rotates around, and draw that here, as the tire rotates around, that magnet will hit the sensor every time it goes around. Now, and then it'll show you how fast you're going. What we're going to be able to do after this lesson is be able to figure out, how do they actually, how do they calculate what we actually get there in terms of the speed based on the setup there. So if you think about point masses versus rotating objects, right? Bike tire, speedometer setup like we're looking at here. Let's go ahead and draw a bike tire. And in class, I'll show I have a bike tire that I spin, but we'll just illustrate that here. Let's say we have our magnet here and our sensor, and so the tire is going around, and we want to figure out how far we go and then how much time it takes, right? So we can have the sensor there. Let's say that the tire goes all the way around, and let's say it took 1/2 a second, 0.5 seconds to go all the way around. Well, let's say that the radius here from here to here, the radius is equal to, let's say it's 0.25 meters from the center. And it takes 5 seconds for it to go all the way around. And in the past, what we did was, this is 5 seconds all the way around. So let's call that T. That's the period. What we could do is to figure out how fast we're going. We could take the circumference divided by the period. How long does it take for a full circumference to go around divided by the period? But you see the problem here. The sensor is not located all the way at the edge, right? The sensor is just located here. But we know that this part of the tire is going to take the same amount of time to go all the way around as the other part, right? So we know the time that it takes for a full revolution here, and we know that V equals R omega. This is coming from before, so this is linear speed. This is angular speed. And then this is the radius here. So, in this case here with the bike tire going all the way around, we could consider, there's multiple ways to figure out the stuff, but, overall we could figure out, how far we've gone based on the tire here. So in other words, if this is the ground here, and the tire makes a full revolution, it goes all the way around. This bike tire, if let's say it starts here, right, and then this bike tire goes all the way around, then bike tire ends up over here, right? There's a certain length right here that we have from here to here that can match the length of the tire itself, and that would be the circumference, right? So that's what we're unpacking here, what's going on with that. So again, if it takes 0.5 seconds to go all the way around, and we know the radius to this point is 0.25 meters, let's say the radius to the edge here was 0.5 meters. That'd be a big tire, but that's okay. 0.5 meters. We could do the circumference, which is 2 pi r 0.5 divided by the period, which is 0.5 seconds. And this would be going, how many meters per second here? Let's do that. It would be essentially 2 pi here. So 6.28 meters per second, right? So that's how fast we're going. We could have that in miles per hour. The converse way to look at that would be to say, okay, I know it covers a full, 2 pi radians, right, for omega. So omega is, how far, the full revolution in a certain amount of time, right? So how much theta in a certain amount of time. So let's say it goes all the way around 2 pi radians in how much time? 0.5 seconds. And so we would get the 4 pi there, right? So 4 pi radians per second. And then if we take that, that's the angular speed, we can bring that in here, which is the angular speed multiplied by the radius. So the radius of this tire, right, is 0.5. So 0.5 times 4 pi radians per second. And then we would get the same thing, 6.28 meters per second. So this just kind of shows, where we're, there's a little bit of review, where we're dealing with, how far does the object go, and that there. So that's good. Okay, so now let's take a look at this here with the body rotating about an axis. You could draw this out. The time that it takes to go from here to here is the just a certain amount of time, change in time. Angular velocity, again, we're dealing with the how many radians we cover in a certain amount of time. So we've got that. The instantaneous angular velocity is important as well. So this is average. If we look at maybe as the tire goes around, it's speeding up, slowing down, or whatever, we can look at the overall radian change. Let's say, went from here to here. We could look at this angle theta, see how much time it took. This would be average. So that's what that bar means at the top, average. Instantaneous has to do with that at that very moment, where the limit as time approaches zero, what's happening. Okay, so what we'll do is a sample problem here. In class, I have the tire and I'll spin it. But we can practice that here. So let's go ahead and spin the tire, and let's say that the tire length here to the radius here from here to here is 0.6 meters. And let's say that we start our timer and it takes 10 seconds to go around 5 times. And what I want you to figure out is what was the average speed of this tire during this time interval. So go ahead and pause the clip and give it a shot here, and then when you're ready to check, you can hit play to continue. All right, so we know average angular speed is how much angle in a certain period of time. And so there's a couple different ways to do that. We could I'll go ahead and show the way that if we use the entire time, we could do that. So if we went around 5 times, we know a full revolution is 2 pi radians. That's all the way around. So we can multiply that by 5. So that would be the total angle. So the total angle would be 5 times 2 pi radians. It's 2 pi radians. And then the time period would be 10 seconds. And so if we did that, and 31.4 divided by 10, that would be 3.14 radians per second. Okay, and then if we did it this way, where we said, okay, I know it goes around 10 times, or 10 seconds goes around 5 times. So that means every time 10 divided by 5 takes 2 seconds to go around. So average angular speed, just one time around, 2 pi radians in 2 seconds, and we'll get the same thing, 3.14 radians per second. And so we actually don't really need the radius until we compare this to linear, which I like to do in class as well. So how far did it go, right? If that's the average speed, we can do that, and so we know, v equals r omega. So if we know the average angular speed, which is this, and we know the radius of the tire, which is 0.6, we can get the average linear speed. So how many meters does it cover? So 0.6 times 3.14 is 1.884 meters per second. So what that means is, on average, it's covering over the ground, flat over the ground, 1.844 meters as it goes. Now we're going to talk about angular acceleration, and average angular acceleration is how the angular velocity changes in a period of time. So we know we have radians per second in a period of time that it changes, so it would be radians per second squared. And then the instantaneous angular acceleration at that moment, exactly how is the acceleration changing? And so we have that there. The average angular acceleration, as we look at that, will help us determine, what's happening with the motion, similar to what we did with linear acceleration, where the object's getting faster or slower. And then the instantaneous angular acceleration will help us see what's happening at that moment. And so when we look at linear versus rotational, it's helpful to compare the different things. Position, S or X, use both in class. Angle is the equivalent in angular, right? So what's the position like if I'm standing here and if I end up here, right? And then this is 0 here. Let's say this is 5 meters. That's my position change. In terms of an angle, if this is right here, we start at 0, and then we go over to here, and let's say that's 2 radians. I could say 2 radians is this location right here. And then linear velocity, that's how fast we're going. So let's say we're traveling, we're running at 2 meters per second. And versus the angular velocity, let's say this is, as it goes around, every second there's 1 radian, so 1 radian per second. So after 1 second, 1 radian, and then after another second, another radian, after another second, another radian. And then acceleration is how that rate is changing. So if I'm going 2 meters per second and I'm speeding up and I'm going 4 meters per second in a period of time, the same can happen rotationally, where maybe we're just going 1 radian per second, but then we're getting faster and faster and faster and faster, and then we start going faster around in a circle. So we have equivalent equations based on what we're doing. So we have on the top here, this was our position and the initial velocity. U is v initial, that's how fast we're starting out. S is how far we've gone, or delta x. Acceleration is the linear acceleration. And then over here, right, the position, the angular position is known here. This is the initial angular speed. Like in that last one, we were going 1 radian per second. And then this is how much faster it's getting in a period of time. And if you notice, everything's the same except those variables. We can look at the how far we've gone, again, delta x. U is the initial velocity. V, just V on its own, is V final. And then on the right side, again, this is the location where the angular location. This is the initial angular speed. This is the final angular speed in a period of time. The third one that we have here, the V final, right? V final equals V initial plus acceleration times time. And then on this side, the final angular velocity, and then equals the initial angular velocity plus acceleration times time. And then here, V final squared equals V initial squared plus 2a delta x is what we're used to. Delta, or just S, is the symbol for displacement. And then another one. And then here, the final angular, how fast, angular speed, initial angular speed, and then the angular, how the angular acceleration is changing, and then the location of in terms of rotation. And so, yeah, they work the same exact way, and we can use that for different various problems. Okay, so let's try this one starting out. The initial angular speed of the disk is 24 radians per second. The disk suffers an angular deceleration of 3 radians per second squared. How many full revolutions will the disk make before stopping? And how much time will it take for the disk to completely stop? So let's go ahead and draw this out. And we have to identify what our variables are here. We know the initial angular speed is 24 radians per second. So that would be the initial angular speed. Actually, that's not right. It should be omega. Omega initial is 24 radians per second. And we know the angular deceleration, and I forgot to mention this earlier, it's kind of that Greek letter alpha that they give for that, not A, but alpha for angular acceleration. And it's decelerating, so we'll have negative 0.30 radians per second squared. And how many full revolutions will the disk make before stopping? So that's theta. We want to know how far does it, how many times is it going to go around in radians. And we can look at the revolutions as well. And then how much time will it take for it to come to stop? So once we have our variables set up, we can find the equation that we need. So if we look at the final, we know that the final is going to be 0, right? We know the initial angular speed is 24 radians per second. We square that. We know the deceleration is negative 3 radians per second squared, and we can figure out how far it goes. So when we do that, we'll get 96 radians. So that's the total amount of radians that it takes to go around. And if you remember, right, for full revolution, if this is 1 radian, right, this arc length matches the length of the radius here. If that's 1 radian, we have 2, 3, 4, 5, 6, and a little bit more. So 2 pi radians is a full 360 degrees. So we can get that in a second. Actually, let's go ahead and do that because I just talked about it. So 96 radians divided by the 2 pi radians, and this again is for a full revolution. 2 pi radians. So 96 divided by 2 pi radians, 15.27. So that means it makes how many full revolutions would be 15, and then just a little bit more. Now if we want to find out how much time it'll take to stop, we can use another kinematic equation for rotation. We know the final angular speed is 0, the initial angular speed is 24, and the change is negative 3 radians per second squared, and we end up getting 8 seconds for how much time it'll take to stop. Okay, so let's try this one. We have a record that's spinning at 33 1/3 revolutions per minute. When the power is turned off, it takes 1/2 minute for the album's rotation to stop. What is the angular acceleration of the phonograph album? So in this case, we're given something a little bit different. This is how many revolutions it makes every minute, which we're going to need to be able to get into something we can use with radians per second, right? How many radians per second is it going? And so when we set that up, 33 1/3 revolutions per minute, and we've got our time, and we're trying to find the acceleration, right? We can set up, we know that the change in angular speed over time will give us the acceleration. And so this also comes from, omega final equals omega initial plus alpha times time. So same thing. And so we know how many revolutions per minute. So we're going to need to go from a revolution to a radian. So 1 revolution, right, is equal to 2 pi radians, because, a full revolution all the way around, from all the way around, is 1, 2, 3, 4, 5, 6, and a little bit more radians. and that's 1 revolution, so we have that. And then we want it per second, so 1 minute is 60 seconds, and we can get how far, well, we got revolutions per second, and then here is, yeah, so 3.493 radians every second, and that is omega initial. That's the initial angular speed. And once we have that, it's pretty straightforward. We know the final angular speed is 0. We know the initial angular speed. We know the time. So the acceleration is 0.116 radians per second squared, and that's the how quickly it's slowing down. And it's negative, if you notice that as well right here, because it's decelerating. All right, so on this one, we have a wheel that's 0.8 meters, and it's rotating about its axis with an angular speed of 2.5 radians per second. And we want to find the linear speed on the point of circumference on the wheel. So you should be able to remember how to do that. So go ahead and pause and calculate that. And then when you're ready to check, you can hit play to continue. Okay, so looking for linear speed, we know the radius, we know the angular speed, and we know the linear speed equals the radius times the angular speed. And in this case, it's going 2 meters per second. Okay, so if the wheel starts to slow at a rate of 0.35 radians per second squared to a stop, find the angular displacement and the linear displacement of that same spot. So yeah, what I want you to do is you can go ahead and try this with the things that you know now, and yeah, give it your best shot here, and then yeah, hit play when you're ready to continue. So go ahead and hit pause, and then you can try it. All right, so we know that the final velocity and the final angular speed is 0. So if we set up the angular speed final squared equals angular speed initial squared plus 2a theta, which theta again is how far it goes, and we can figure out how far it goes. So theta comes out to be 8.929. I'm trying to read my handwriting. I think it's 929 radians. And then in terms of linearly, we could do the same thing. Now in this case, this is where we're going to introduce this to you. You can also do this. We can find the angular acceleration and linear acceleration with a similar relationship as this equation over here. If we take the radius and multiply it by the angular acceleration, we'll also get the linear acceleration. So you could have taken this and set it up to how long is this in linearly, right? For 8.9 radians, so going all the way around, figuring out the circumference and doing that. Or you could just do this. So if we do this, we'll get the angular or the linear acceleration is negative 0.28 meters per second squared, where there we can find out how far it goes, 7.14 meters. So in other words, over the ground, this car would go this wheel would go 7.14 meters, and it would cover this many radians as it circled around there. All right, so for part C, we want to compare how does the angular and linear velocity compare at 0.4 meters. So in other words, right here, 0.4 meters away from the rotation point, which is in the middle, how does that compare to the 0.8 meters away? So you should be able to do that. You can go ahead and calculate that, and when you're ready, you can check. So go ahead and hit pause, and then when you're ready to check, you can play to continue. All right, so you should recognize that they both have the same angular velocity. So as it comes around, let's say it's going around like this at this point, and this one's coming around like this. They both cover the same amount of radians in this, right? So the angular velocity is the same. It's the linear that changes, right? So we know v equals r omega. And so for the inner one, we'd have 0.4 meters times the angular, which is 2.5 radians per second. And for this one, we end up getting 1, okay? So 1 meters per second. And then for the outer one here, we would have, again, v equals r omega, and we have r as 0.8, omega 2.5 radians per second. and that will come out to be 0.32. Wait a minute. Oh, I divided. 2 meters per second. So yeah, so it's the outer part is covering twice as much ground. You know, this as it travels around here, twice as much length as the inner part. And if we would have set up a ratio between the two, the new over the old, yeah, we could have done that, and we would see that the linear velocity is half for the inner one.